The broadcast is now starting. All attendees are in listen-only mode.
Good morning. This is Mark Richardson at Vibrant Technology in Scotts Valley, California. It's 9 o'clock in the morning, and welcome to all of you that are sitting in on this webcast. We're going to spend the next hour together, and I'm going to demonstrate two new features in Emscope. What we call macros or macro programming. We used to call it programming now, and it was an option. Now it's a standard feature in Emscope. And along with the macros, we now have some new features called hotkeys, and those are also part of the macro programming. Basically, a hotkey is something that I can create, and it will show up on the toolbar up on the top of the Emscope window here, and I can press the hotkey and automatically execute one of the macros that I've designed. We're going to look at two different projects today that are all set up and ready to go. I'm going to explain to you the macro programs that I've written for these two projects, and we'll see how they process data. Now, the first project I'm going to open here is called Vtec Animate 2 Orders using hotkeys. So this is Emscope, and we're in the work area with the start page, and I'm going to click on this recent project here and open it up. Now, we had a request last week for a capability like this, and from a customer who wanted to see an ODS animation of the first two orders of a machine. So we happen to have a small machine here at Vibrant that we can use to take data, and here's a picture of the setup. Okay, it says it's pausing the screen sharing. I'm not sure you'll be able to see that, but this is a picture of our setup of the machine. Let me see if I can put that up. Does that not come up? Open. Oh, that won't come out. Here. We're having a little technical difficulty here, so let me see if we can show you this picture a little better. Show my screen. There. Oh, there we go. Okay. So, little technical issue, but this is what's called a Vtec Rotor. We purchased this from a company, Vtec, down in Atlanta, Georgia. This is very handy for looking at ODS data on a rotating piece of equipment. Here you can see a tachometer, and there's a piece of tape on this one rotor, so we can actually measure the speed of the rotating part of this machine. You can see accelerometers located. There's actually 8 triaxial accelerometers on this machine. 1 on each of the bearing blocks, and then 3 down this side of the base plate and 3 down the back side of the base plate. So we can collect with a multi-channel analyzer 24 channels of accelerometer data as this machine operates, together with 1 channel of tachometer signal. So let me show you some of that data. I'm going to come over here, and under the project, here is the pre-recorded data that we took off of the machine. You can see there's 25 channels or 25 traces. So 1 through 24 are the 8 accelerometer locations, and with the triaxial degrees of freedom, X, Y, and Z. The units are Gs, and then the 25th channel is the tach signal. So if we scroll through this, and this data was taken when the machine was running at 1590 RPM. So I'm going to scroll through some of this data. You can see it's very random in nature, but when we look at the spectrum of these responses, you'll see that there are orders. Now there's the tach signal down there. If I zoom this in, you can see that the tachometer, when it sees the reflective tape on the rotating wheel, it puts out approximately a square wave. So that's what we use to determine the speed of the machine. All right, let's take a look then at the spectra that we got off of this machine. And here are the spectra. Again, there's 25 channels, 1 through 8 with XYZ, and then the 25th channel is the tachometer signal. So let me scroll down here to there is the tachometer signal, and if I have the peak cursor on here, and you can see that the peak or the order cursor together with the peak cursor. Now the peak cursor is set here at the running speed of the machine, so you can see that the speed according to the tachometer is 1590, and then the red dots are all of the multiples of the running speed. So this first red dot here would be the first or the second order. We call the running speed the first order, the second order, the third order, and so forth. So this is the data that we acquired ODS, or operating deflection shapes, from. So let's go ahead and look at some of that data. Let me open up the model. So here's a model of the Vtec Rotor with the 8 accelerometers indicated on it. And I'm going to call up the orders. Here we go right here. And let me see that data. Okay, so here are all the ODSs that have been saved for or from the spectra that we just looked at. So we simply did a save shape and saved this data from the data block into the shape table here. So let me begin the animation so we can just look at some of these shapes. So here's our model. It's rotating, and we can look at it in different ways. If I look at the quad view of it, well, let me see if I can get everybody to center a little better so we can look at this. So you can see that the first order of this machine, the running speed here at 1580, is what looks like a bending mode. Let's go back and look at it again here. And so there's a bending mode of the bottom plate, pretty much. Let's go to the second order now and look at that. Quite a different motion here. Now the bearing blocks are moving sort of out of phase with one another, and there's a little bit of twist in the bottom plate. So the question that one of our ME-scope users had was, what would the ODS look like if I had the two orders summed together? Now the only way we can do that is not in the frequency domain, because there we could only animate one frequency versus another, which is what we're looking at here, the ODS data. But we need to do it in the time domain, where the summation of the two orders, the deflection at these two different frequencies, is summed together. And then we can animate this model by sweeping through some time domain signals. So that's what we're going to do with macros here. Let me stop this, and I'll put this down. And now over here is a macro, and this program has already been created, and we'll execute it here in a minute and look at what it actually does. So the first step here in the macro, well, let me explain a little better what macros actually are. A macro is a spreadsheet, as you can see it here, and in this spreadsheet is a target window. This can be any Emiscope window, a target command, a target window command. This can be any window command in that particular window. And then over here is a description, and we can open dialog boxes and enter data and so forth. So you can see that most of these commands in here, I don't need a data block. I don't need a dialog box. I have some other steps here, and this is a spreadsheet that I can select steps, and I can edit them and reposition them, and I have a number of editing tools up here for using with a macro. You can see this one step here has a no, which means it will not execute. We'll turn that on in a minute when we run the macro and see what that does. But let's just look at these few commands here, and I'll explain them to you briefly. And I think when we run the program, you'll get a better idea of what it's doing here. So the first step, all right, well, this is another feature here, is that I can look at this window if I change the macro options so that I display the macro and the target window together. So I'm going to do it in a left-right format. So this was in my macro options box. So now when I click on this, it's going to show me a data block with a single sine wave in it. Now I synthesized this sine wave using the new data block command. So that command is up here under the File menu, New Data Block. Now when I use this command up here, it gives me a lot of different options. I simply chose the one that allowed me to generate a single sine wave, and so number of traces was 1, a single sine wave with an amplitude of, or a magnitude of 1. So I've already done that. Let me go back here and click back over here. Okay, what happened to my sine wave? There it is. So this is a sine wave with a certain frequency in it. What is the frequency? Well, it says 1590 hertz, or 1590. So that would be RPM. Let me just show you that very quickly. I'll FFT it, and we're going to zoom down here. Here's a peak in the data. I need to change my x-axis to RPM so you can see it in RPM. And if I put the cursor over there, there's the peak at 1590 RPM. So that is my sine wave. All right, now I'm going to come back over here to the macro program, and you can see the next target window is in fact the macro itself, and it's going to define a variable called counter. And then the next step, it's going to set the counter equal to 2, and now it's going to begin a loop. And the loop is going to go back here to the sine wave window and copy traces to the file, to a file. And where's it going to copy them to? It's going to copy them into itself. So it's going to add this sine wave to itself, and this is a way of building up. That command there is turned off, and we'll turn it on in a minute so we can look at it. And then it's going to come to a logic statement that's built into, or this is an arithmetic statement that says macro variable 1 is equal to variable 2 times an operator times 3. Well, what does all that mean? This is programming. So if I come down here below, you can see variable 1 is the counter variable. Variable 2 is the same variable, and the operator is an add operator. So if I look at my pick list here, I can add, subtract, multiply, and divide. So what I'm doing is adding 1 to the counter each time I execute that macro. Okay, the next command is a logic statement. And here's what it says. It says, macro variable 1, if variable 1 compared to variable 2, then go to step label 3. Now here's a little problem down here. This should just say compare here. It has a different message in here, but it says counter. If the counter is less than or equal to 24, then go to the step label, in this case loop. So here's a step label right here. So this little 4 lines of code here in this macro is going to loop 24 times. And what that's going to do is fill this data block up with 24 traces with the same sine wave in it. So what are we doing that for? Well, let's go on. The next step says, now I want to copy the degrees of freedom from the data block, and no, this is the shape table. I'm sorry, this is the shape table with the orders in it that we were animating previously. That had the degrees of freedom 1x, 1y, 1z, all the way through 8x, 8y, and 8z. So it's copying these degrees of freedom, and this is the position in the spreadsheet of those degrees of freedom, and it's going to then unselect all the traces over here. So you can see that there's actually 24 of them in there, and then it's going to paste from the clipboard those degrees of freedom in. So right here, rather than a 1x, it's going to paste in all of these degrees of freedom from the shape table. So the degrees of freedom in the data block will match the shape table. Then it's going to go to the shape table and select the first shape. So down here it says parameters, shape number 1, select it, unselect everybody else first, so you can see that it's selected the first order. Here it's going to transform this data to the frequency domain. We looked at that. That's going to show us the Fourier spectrum of the data. Then we're going to scale the traces by the ODS data. So instead of all being an amplitude of 1, now you can see as I scroll through here, these traces have already been scaled. Instead of having an amplitude of 1, they've got amplitudes that match the ODS amplitudes. So if I animate this data by itself, I can then see the ODS of the data from the time domain, as opposed to where we originally got it from the frequency domain. So we're going to do the multiply in the frequency domain. That preserves the phase of the complex ODS data. We scale it, and you can see that we're going to use a shape table with the orders in it. And since we've selected the first order, it's going to use that data. And it says use shape table, and then it's going to the destination. Well, I'm operating in this data block, and I'm putting it back there so you can see what happened. And here, then we're going to inverse Fourier transform, and you can actually see the time domain. Then we're going to animate the data, and we'll position the structure window to be half of our space here. This is a positioning command, macro window position. And then we're going to arrange the windows for animation. So this program is going to automatically do all this processing. And how will it do that? Well, up here you can see that I've got 3 macros already defined. And the first one's called first order, then second order, and then 2 orders. So that's the one we're going to eventually get to, that will sum the two orders together, and then we can animate the model with the first two orders in our data. So how did I define these macros? Let's go over here under the macro command, or the macro menu of commands, and here's something called hotkeys and hotkeys setup. So I'm going to open that, and here's where I define, this is another spreadsheet. You can see I got a plus sign up here. I can add more hotkeys anytime I like, but this one's already been set up with 3 hotkeys. I named them first order, second order, two orders, and here's the macro that's going to be executed when I press that key. So again, I can pick any one of the 3 programs. I've got a program called a macro called first order, second order, and two orders. So let's go ahead and run this and see what we get when we press the macro. I'm going to close this, and we'll simply press this button up here, and you'll watch it'll race through here very quickly, and when it gets down here it's going to animate the data for us. So let's go ahead and do that. You can see it building the data block, changing the DOFs, and bingo, there it is. So we have done all that with that macro. And there it is, animating the first order from the time domain with a sweep operation through the 24 sine waves. So there's an ODS, what we would call a time domain or order-based ODS of the first order. All right, well, we have a similar program for the second order. There's 2 orders. Here's the second order. So this program is very similar to the one we just went through, except now it's going to take a different sine wave. Let me see if I can get it to come up here. I have to turn on the display together. And so there it is. Here's a different data block with a 3180 RPM sine wave in it. So again, we can look at the FFT there, and we'll see a peak at 3180 RPM as we saw before. So this is going to, again, this program was easy to write because I just copied all of the instructions from the first order into this program and then renamed some of the window names. So now I'm dealing with the second order and a 38 or a 3180 RPM, which is the second order. So let me go ahead and run this one now. I'll go up here and press the second order, and it's going to run that program. Okay, so there it is. Now I didn't quite get what I expected here, but let's just rearrange things a little bit. Okay, so there it is. There's animating the second order. And you can see that it looks very similar, and in fact it should be identical to the ODS for the second order, because this data over here in this data block has been scaled by the second order ODS. So there's another time domain animation of the second order. I'm going to stop the animation, and let's go look at how we sum these two together. Well, I can't find what I'm looking for, so I'll hit the arrange windows, and here's a program called two orders. So that's my third one here that I'm going to execute with this third macro or third hotkey button. It's going to execute this macro here. So Let me expand that so we can take a look at it. Now what it's going to do is take my my first order data, the 24 traces, and it's going to FFT them first. So we're going to sum these two time domain signals together in the frequency domain. That's where we preserve the magnitudes and phases of these two signals. And then we're going to copy them into another data block, the 1590. We're going to copy it into a destination block called both orders. And we're not going to use the cursors or anything in this case. So these are standard commands. Copy traces to file is a standard edit command in it from the data block from the edit menu. Then I'm going to do the same thing for the second order, the 24 traces defining the second order. And here we're going to do in the both orders where I've already got the first order. Now I'm going to add the second one. So that's what this command is doing here, match add a trace, and that's the standard data block command in ME-scope. In fact, all of these are commands right out of a data block in ME-scope. Now the transform commands are one of the, that's an ODS Pro option that wouldn't come in the standard ODS package, but the rest of the macro capability is certainly available for doing the animation, but some of this processing would require some of the options. Here we have the both orders. We're going to use a save method, and we're going to operate on what's already in there, the first order, and we're going to operate, we're going to add here, it says add a trace. So we're going to add this trace to what's already in there, which is the first order. So there's where we're summing the two together. And then we're going to inverse Fourier transform these two back to the time domain as well as the both orders. And then we're going to animate the shapes. So let's go ahead and run this macro, and I'll go up here to this hotkey and press this button right here. Okay, let's see, we need to kind of arrange things here a little bit. Let me draw this over and push the arrange button again. All right, well, I want to get just a few things up here, and let's see if I can arrange it so we can animate all three. But there is both orders animating now. So there they are summed together, and you can see that there's still the bending mode in there of the first order. It's still dominating, but we also have some of the effects of the second order. The second order was a little bit of out-of-phase motion of the two bearing blocks. So this is showing the summed capability, or the summed effects of the first two orders. As I scroll through here, you can see these time domain signals look quite different. They're no longer simply a sine wave, but they are essentially the sum of two sine waves, but with different amplitudes and different phases. Again, the first order is certainly dominating in this data, but in many machinery applications, the higher frequency orders may be the ones that we can use to diagnose bearing problems or misalignment problems or soft foot, other issues that occur with rotating machinery. Now I can go back and let's get these three up here. We got that one, and there's the 3100, and let's get rid of that. So I've got three of them now. I ought to be able to arrange all three. So there's the sum of the two orders. I can go back here and just click here, and this will animate the first order. So there it is with the two bearing blocks moving together and essentially bending of the bottom plate. Here's the second order, quite a different motion. This inboard bearing block is moving a lot more than the outboard, and the outboard is more of a twisting motion here of the base plate. And then I can click down here and see the sum of the two together. So there's an example of using three different macros with three different hotkeys, and looking at the first order, the second order, and then the sum of the two orders using time domain animation. All right, let's go on to the second example. We're going to do a little bit different analysis with the same machine using some different data that we collected, and we'll look at some different macros and a different capability that is also available in MeScope for animating models like this. This model has a lot of points, and it's got some rotating substructures. You can see all these different substructures in here, and they're running at different speeds. The motor pulley is running faster because it's smaller. You can see that it's rotating around faster because of the difference in diameters. So this has all been built in MeScope and set up in MeScope to animate. And when you have a complicated model like this, it's easier to put your accelerometers as points in space and then use the interpolation in MeScope to interpolate between the accelerometers. And even in this case, you can see this one accelerometer here is oriented in some strange directions. Again, it's a different type of an accelerometer that we mounted so that its X and Y are at 45-degree angles, whereas these other accels are pointing in actually in different directions also. Let's go on to the second model, and we'll talk about what I just mentioned here a little bit more. I'm going to close this project, and I won't save it. Now, those hotkeys and macros are all part of the project, so I can come back anytime and run this over again, take these macros and modify them a little bit, and use them for different sets of data. I'm going to open this project here called 3 Speeds. Now you can see we've got a whole bunch of stuff here. What this project has in it, again, let's look at our experimental setup. This is where we took the data. For those that you got here a little bit late, we saw this in the previous project. This is our experimental rotating machine with a laser tachometer so that we can measure the speed of rotation. And then we've got triaxle accelerometers. There are 8 of them on here, 1 on each bearing block, and then 3 down this side of the base plate and 3 down the back side of the base plate. And then we got a variable speed controller here so that we can control the speed of the motor and change speeds. So what we did here was we took actually 3 sets of data, and we're going to use an FEA mode shape model. And I won't go into all the details of how we did this, but I'll show you the model, show you how we built the FEA model for the base plate and the bearing blocks. And we're going to use that to drive the animation and use the interpolation then from that FEA model to animate the Vtec machine model that you see here in the picture. This is not the one. Let's get the same model that we were just working with. This is the model that has the spatial interpolation between the 8 accelerometers. And here I have some shape data. Let's just see what that looks like. 3 speeds. So here's some ODS data. 24 degrees of freedom. There it is. 24 degrees of freedom in the mode shapes, and or not mode shapes, but ODSs, and they were taken at 3 different speeds: 985, 1440, and 2280. So let's start the animation, and let's just look at these ODSs here. Okay, so there is the machine moving at about 1,000 RPM, and you can see that it's really most of the motion is just horizontal, and we've set the rotation speed of the parts at the same speed as this first running. Oh no, it's at 1400. So when I go to the 1400 shape, that shape there is the parts are rotating at the same speed as the animation. So there we can see the order-based motion of the machine. Now it's quite exaggerated. Maybe a little less amplitude would be more realistic. And you can see that the bearings and the shaft are moving. They're following the 2 accelerometers on the bearing blocks. So this, we get a little bit of exaggerated motion there, and maybe not so realistic because of the interpolation, the way we set up the interpolation equations. But generally speaking, the way the interpolation is set up is that we take the motion of the 8 accelerometers themselves. In this case, we take the bearing blocks first and animate the shaft, and then turn those animation equations into measured, and interpolate the rotors from the shaft so that they follow it, all 3 of these rotors, including the pulley, and work through the model one substructure at a time to set up the animation and then also the rotation. I'm not going to go into all those details today. We have another YouTube video where we show more the details of setting up this animation. But you can see the ODS of these machines at this machine at these 3 different speeds is quite different. There it is at 2200. Quite a different motion. There are 4 rubber mounts under the corners of this machine, and plus it was sitting on a rather flexible table. So the machine is showing a lot of rigid body motion simply because it's bouncing on the table and on the rubber mounts of the machine itself. So this is an ODS, not necessarily a resonance in there, although the assumption is that if there's any flexure in the machine itself, let's go up here a little bit higher frequency. Certainly there we start to see some twist and some flexure, maybe bending of the bottom plate as we saw in the previous example. What we're going to do here is take some mode shapes of this machine, and we're going to curve fit them to the ODS data, and we call this shape expansion because the mode shapes are defined for the entire base plate and the bearing blocks, and this we did in Emiscope, very easy to do. And so let me show you that. I'll put this down, and here's one called the expanded model, and I'm going to animate some mode shapes on this model. So let's bring those up, and I'll put them over here so we can see them together. Now these mode shapes have almost 2,000 degrees of freedom. Here you can see the M number is at 1938. And they've been, animation equations have been created so that this model here will animate these mode shapes. So let's start the animation. Now, go back here to the animation. All right, so there is a rigid body mode. Well, where did I get these mode shapes from? You can see I've got a number of substructures here in this model, all the different parts. There's 26 different substructures. But the top one up here, there's one called FEA model and another one called the Vtec Rotor, which is what you're looking at. So I'm going to make the model visible, the FEA model, and hide the rotor. So here is the FEA model that we built of the base plate and the bearing blocks. And here I'm sweeping through the shape table. This is standard in Emiscope. I can just turn on the sweep. The first 6 modes are rigid body modes, which the FEA solver gives us when we populate these 2 pieces of the machine with, in this case we use brick elements and a few of the other solid elements in Emiscope. Very easy thing to do in Emiscope. Let me explain one other thing that we did, which is very simple, and that is, here, let me just stop this for a second so that I can explain this. We built a FEA model of the base plate that's dimensionally correct and made of aluminum and so forth. That's easy to do in Emiscope. And we got the 20 modes of the base plate using our experimental FEA capability right off of the display model, the machine model. Then we built an FEA model of one of these bearing blocks, duplicated it, and put a copy of it over here. Again, this is easy to do in Emiscope. Then we took the FEA modes of the 2 bearing blocks and the base plate, and we connected them together using SDM. Now normally in finite element analysis you would have to match up all the points on the bearing block with the points on the base plate. With SDM you don't have to do that. You simply attach each of these bearing blocks to the base plate using very stiff springs. So that was done in here. Let me just show you very quickly how that was done. I'm going to go up here and well, I don't even see it up here, so I'm going to go display. Oh no, I want to edit. Oh, here's my problem. I'm still animating. Let me stop the animation. Now I'm going to go look at springs. So here are all the springs that were defined in order to attach the base plate, the bearing blocks to the base plate. There's 36 of them. And you can see that they're in different directions so that they stiffen the motion between the modes of the bearing blocks and the base plate. So that's how that was done. Let's go back to the animation here again and look at these different modes. So the first 6 modes are rigid body modes, and then we've got 4 flexible modes. We're going to take this modal model and curve fit these mode shapes to the ODS data, and we call that shape expansion. And when we do that, we then get an expanded ODS that we can animate on this model here. of the structure. So I'm going to go ahead and turn the rotating machine back on and turn the FEA off. So this model here, the rest of the model is being interpolated from the FEA model that's underneath, and now I've hidden it so you can't see it, but the animation equations are still there. All right, let's look at the macros. We've got 3 macros up here, and they're called first shape, second shape, third shape. Second shape misspelled, third shape. Let's look at what the first shape does. Here's the macro for the first shape. Well, it's got 2 commands in it. This is a command in the window itself. It says macro variable 1 in macro equals variable 2. Well, that's some strange language here, but it's better to go over and read the description. Sets variable 1 in another macro equal to variable 2. So I come down here, and here's the other macro, and this macro is called expand the ODS. And variable 1 is the name of a variable in the other macro. And I'm going to set that equal to variable 2, which is 1. So this is just a little programming command that says set that variable in this other program called expand the ODS and run that macro. Executes all enabled macro steps once in this one. So we need to go find this expand the ODS and see what that macro is going to do. Let me rearrange again and see if I can find that. I'm looking around. Here it is right here, expand the ODS. So here is the program that's going to do the shape expansion. So the first thing it does is define a variable called hotkey case. And that's the one that was set equal to 1 by the program we just looked at. Then it's going to go into the shape table called 3 speeds. Remember, we animated those ODSs. We had 3 of them in there. And it's going to select shape number HK case. In other words, whatever this variable is set equal to, it's going to select that shape. So in the case of the first, when I click on the up here on the hotkey for the first shape, it's going to set it equal to 1, and it's going to select that shape. Then it's going to take my 10 SDM modes, those are the ones we just looked at, the FEA modes, following the SDM process that I explained to you where we attach the bearing blocks to the base plate, and it's going to do a shape expansion. So here it takes the SDM modes, all of them, and the first shape in the 3 speeds, and because I'm in the 3 speeds window here, I'm going to take the 10 SDM modes and I'm going to store the result in a destination called expanded ODS. So I'm going to put them in there. 3 speeds, I'm going to, okay, this is going to select the first shape again, and that's the same as this command up here. It can do it over again just to make sure it's selected, and then it's going to position the expanded shape model. This is my structure window that we were animating the mode shapes on, and then it's going to do a compare shapes between the expanded ODS and the 3 speeds animating on the interpolated model, the geometrically interpolated, the ones we looked at first. So we're going to have 2 models two different models animating, and let's go ahead and just run this and see what happens. So I'm going to go here, and I pressed on the first button, and bingo, there it is. So now what I'm looking at here is the expanded shape on the left at 985 hertz or RPM, and over here, I'm looping through the three of them down here. So let me change that so we're not sweeping. I want to do a sine dwell. So here now I need to click. So on the right I have the expanded shape. You can see it's nice and smooth. On the left, on the right, I have the geometrically interpolated shape data with the 24 degrees of freedom, and the Mach value is 87%. So a very good match of the expanded shape at those 24 degrees of freedom with the actual experimental data. And what we did is we curve fit all 10 modes to that data. So having those rigid body modes in there, you can see that we got a good match. Let's go and click on the second shape. Now all that's going to do is run another program, and now I'm looking at the second shape. So there's the second ODS at 1440, and a 91% agreement between the curve fit results over here on the left and the simply the experimental data itself. And then I'll click the third shape. I'm going to run another macro, and all I'm doing is changing the case from 1 to 2 to 3, and then running and then calling the same program. And this one is 94%. So at 2280 RPM, you can see that we're looking at the 3 speeds down here, and up above we're looking at the expanded ODS with the 2000 degrees of freedom in it, and that is a comparison of the two. So the expanded shape capability, once I have a set of mode shapes, I can use those to expand any ODS data no matter how many degrees of freedom. Now of course I'm doing a curve fit here, so the more points I have in the experimental data, the more accurate the curve fit will be, and also the number of modes that I use in my modal model is going to influence the curve fitting. Let me show you one more thing here, and then we'll take some questions. Brian, if we have any questions that people have sent in. Let me just run these cases again. I can go back here and run these macros as many times as I want. Once the programming is done, it's saved with the project, and I can run any amount of data through. So the idea with a macro is that I'm doing a lot of emiscope steps by just pressing a hotkey here to look at my results. And let me do the third one again. I'll stop this and show you one other thing that kind of explains what we did here. If I come down here and get, now shape expansion is one of the commands under the tools menu. Shape expansion, there it is in the structure window, or the shape table window. But one of the other commands I have in here is something called participation. Now this is going to show me the participation of those mode shapes in each of the ODSs. So let me go ahead and execute that, and it says you've got things selected here, and I do. I have the third shape selected. So let's unselect all those, and let's select another shape table for shape participation. So I'm going to select my 10 SDM modes that we looked at earlier in animation. And here's what we get. This is a picture. It's kind of like a Mac window. This is a matrix of the scale factors. We call it a participation matrix of each of the 10 mode shapes in each of the 3 ODSs. So if I put the mouse over here, I can see that this is my shape number 1. If I put it up there, that's mode shape number 1 at 54 RPM. Now the RPMs don't matter here, just the mode shapes. That's an interesting thing about shape expansion. I can use these FEA mode shapes that perhaps don't have the right frequencies, but their participation in the ODS, these are the first rigid body modes. So you can see for the first shape, if I count across here, 1, 2, 3, the first 3 rigid bodies, the 4th and 5th don't participate, but the 6th one does. And then I've got 4 flexible body modes here, and they participate also in the ODS. So this is showing us how these mode shapes are used to curve fit the ODS data. And here's a second case here where I've got a different participation of rigid body modes, very little of the flexible body. And then the third ODS at, this one's at 2280, a different participation again of the modal model. Now I can use as many modes as I want, but as I go to higher frequency mode shapes, they're only going to curve fit at the degrees of freedom where I have the ODS data. So I may not want to use too many modes in the curve fitting process. All right, I guess that's all I had to say. Brian, do we have any questions from the audience?
No questions have come in.
All right, well then I'm going to terminate this webinar and wish you all a good day wherever you happen to be today, and we'll be on the air next month with another webinar showing you some more features in Emiscope. Today we covered the macro programming and the hotkeys. So have a good day. Talk to you later.